Hi and welcome to another Ember 3D tutorial. The goal of this tutorial is to show you how to define a complex erection sequence for a curved plate girder bridge. So I've got the model already open and actually run here for simplicity, but these are the different features that I have on my bridge. It's a multiple girder bridge, it's curved, it's got stiffeners, X-frames. I'm doing an erection analysis, a buckling analysis for some of the stages. I've got pin and roller supports. I do not have any other load other than gravity loads, like self-weight of the steel structure, and I do have splices on the bridge. It's a curved bridge with a radius of curvature of about 700 feet. The orientation of the curvature is to the left here, so R is really the radius for the interior girder. I do not have any point of tangency or compound curvature. I have 4 girders, okay. The spacing is equal to 11 feet. The material properties are default. I have 4 supports, and the second support is the pin support for all girders. So 1 stands for pin and 0 for roller, okay. I've got 8 splices for the first 3 girders, 10 for the 4th one, and I have entered these values from an Excel spreadsheet. I've just copied and pasted the values in, okay. I've got 28 stiffeners for each girder. Again, this is something that you can either enter manually or from an Excel spreadsheet. 3 here stands for the fact that you have stiffener on both sides of the web. I'm then defining my X-frames. Here are the chord areas. I am not applying a multiplier of 65% on their stiffness. This is something that you would maybe consider for fatigue analysis, live load analysis, but we're not doing that here. And again, I have entered these values from my Excel spreadsheet directly. So you can see that the spacing is equal to about 20 feet. I am not going to click on this button. I could, but I have already run the model. If this is the first time you get to this form, you do need to click on it. You also do need to click on it whenever you change any of these reference points here, okay? And this is for the program to properly mesh your structure between the reference points. The mesh size is equal to about 18 inches. I haven't entered these values myself. I've just entered 18 here and hit apply. And so whenever there is a short segment, for example here, the program will automatically find the most appropriate mesh size for this particular segment. But in general, the mesh is equal to about 18 inches. These are the cross-sectional profiles. I have 16 of them, okay? So it's not a uniform bridge as in previous tutorials. Here is a figure that can help you define these properties. And then I am assigning a particular profile to each of the segments, okay? So this is something you can read on the plate girder elevations. You need to be careful, of course. You want to assign the right profiles to each of the segment. And on the next form, you would enter the left and right elevations. This is a bit confusing the first time you get to this point. You've got this help figure to help you. Most of the time, you are in this configuration where the web depth is constant, so you just need to enter, say, for this segment, -a or -a minus b, etc. But the good news is you don't need to do that yourself. You just hit the default button here, and the program will automatically for you fill the last 2 columns, okay? And that's for that's for all the girders, okay? So -2 here means we're probably in the negative moment regions, thickened bottom flange. Here is the form where I am defining the erection sequence. I've got 8 stages here. So I am first activating girders 3 and 4 up to 200 feet. So that's past the second support. And then I have girder 2, which is activated up to this point. And then girder 1. And then girder 4 to that point. Then girder 3. The last 2 girders here. And then stage 7, I have girder 4 up to the end. And then final one, stage 8, where the whole system is activated. I do not have any drop-in member. This is something I can have as well. I can have any number of drop-in members, but here in this sequence, I do not have any of them. I am turning on the cross frames whenever the girders on the left and right side of the cross frame are themselves being turned on. And so for that, I do not need to enter these values myself, but just click on the default button. In some cases, you may want to wait further to activate the cross frames, even though you have already defined it in the reference point section. And this is because you want to really respect the erection sequence where maybe the cross frames, some of them will be installed after the whole system is fully erected, and then you come back and you erect a few cross frames. Okay, but here I'm following the default assumptions that cross frames are activated when the girders on both sides are themselves being turned on. I am running an eigenvalue buckling analysis for stage 1, 2, 4, and 7, which is why I've got ones on these rows. And here is where I'm defining a search interval for the eigensolver. This is really a shortcut to help the eigensolver. You don't need to click on this advanced button, but this is something I usually do when I have kind of an idea of where the eigenvalue will be to speed up the eigensolver, which may take several iterations if you have a lot of local buckling modes, for example. And that's the final form where you would click on run if you were to run the analysis. In this case, if I've already run the analysis, and the reason for that is we could click on a run, but it would take about 6 to 7 minutes, and I don't think this is appropriate for this tutorial. So let's go directly to viewer. And if you ever hit a black space like this, just click on any of these views here, and you can click on here plus. That means that when you click on the move buttons, the system will shift faster. Let's zoom in. Let's shift the system to the left. You can see I have only 2 girders erected for stage number 1. Let's look at the plate thicknesses. This is something you would always do to check your cross-sectional assignments. And let's look at the linear elastic solution. We have for this stage a maximum displacement of 3.2 inch. The eigenvalue is equal to 4.6, so that's pretty good. That's a global mode, a global ladder mode. Mode number 2 is already a local web buckling mode. Okay, so we're not interested in these modes. We have only defined the stiffeners that we need to attach the cross frames. There may be additional stiffeners on the bridge. We can of course look at the von Mises stresses or the sigma YY stresses. So of course blue here would be compression and red would be tension here on this second girder. On this, actually that's girder number 4. You can look at any other stress component, like a sigma XY would be the torsion in the flanges, and sigma YZ torsion in the web. You can also look at the cross-frame forces. Okay, so here the maximum cross-frame force would be about 4 or 5 kips. We can also look at the support reactions. So here 77 kips would be the largest vertical reaction. Okay, let's click on here and then move on to the second stage, where now the maximum displacement is equal to 2.5 inch, and the buckling mode is actually a local web buckling mode at 5.4. Okay, did I capture any global mode? No, I did not. So okay, so the system is already pretty stable, and the eigensolver would need to grab a bigger interval, bigger search interval to be able to capture the first global buckling mode. Now let's go to stage number 3. And stage number 4 would be there. So let's zoom out and shift the model down and left. Let's zoom out a little bit. Okay, have we run a buckling analysis here? We have 4.8 is the first mode, the first buckling mode, the first buckling eigenvalue, so it is still pretty stable. Let's now go to stage number 5. You see all the cross frames are being turned on, so that's the default option. 3.6 is the maximum displacement. You can of course check any stress here. 12.3 KSI compression here on the top flange, about 11.4 here at the support in tension. Let's go to stage number 6, 7. Let's shift the model down again. I believe we have run a buckling analysis. Yeah, the eigenvalue is equal to 7.9. So this bit here is probably stiffening up this portion of the bridge substantially. So 7.9 is quite high, so that's pretty good. We have quite a stable system here. Okay, and finally stage number 8. So that's when the full bridge is activated, the full steel superstructure. There's of course plenty of things you can do. This button will lead you to the chart showing the displacements. Here that would be the layovers, the stresses. Let's look here, for example, at the moments. So this would be the moment diagram for stage 1, stage 2, stage 3, etc. You get the point. If we go to stage 8, this would be the final moment diagram. If we look at the shear diagram, this is what we would have for the final stage. If we look at the torsion diagram, this is what we would have. Top flange lateral bending diagram and bottom flange lateral bending diagram. Of course, if you're interested only in girder number 4, for example, you would enter zeros here and hit refresh. Okay. You can also look at cross-frame forces. That would be for stage 1 and for all 3 bays. So let's say I want to look at stage number 8 and I just want to look at the diagonals. I would enter zeros here, hit refresh. If I just want to look at bay number 3, which has probably the largest forces, I would just enter zeros here and hit refresh. So you see that for the final stage, the maximum compression in the cross frames is equal to 7 kips, and the maximum tension is equal to 3.4 kips. If I want to go, it may not be the stage where you have the largest forces. Let's check, for example, number 6. Got 9.4, see? So this is a nice way to check your cross-frame forces, which for curved bridge are primary structural elements. So I hope this tutorial was useful. We haven't, of course, covered everything yet. We could have defined a more complex erection sequence with drop-in members, but I hope this is good enough for you to define your own erection sequence for the bridge you're analyzing and at your work or for your project. Thank you.